Welcome to episode 11 of the PM Blend. I'm Mark Powell. This is Joe Finksler.
Hi,
Joe,
Mark.
how are you?
Great. How about yourself?
Joe, I don't know that I could get any better right now.
I don't doubt that.
Yeah. And I'm, super excited about not only the topic today, which is, the questions we most oftenly hear from our customers, our partners, our prospects, but I also love the group we have today.
Oh, this is the dangerous group.
This is dangerous. Yeah.
Good group.
Got Tom Finksler to my right. Tom, welcome back.
Yeah, thank you.
And then Doug Haynes and Phil Parks. Guys.
Hi, guys.
Thank you. It's been a few episodes since we've had you in. It wasn't because we didn't want you.
We're glad to be back.
We found where this is.
Let other people answer questions.
This episode really fits these guys.
Working with you guys is difficult.
Well, speaking of working together, let's talk about just a short relationship here. You two, of course, brothers, have worked together for what, 40 years?
40 years.
Yeah. And these two haven't been here for 40 years together, but how many years have you two worked together?
Close to 30 or about 30 years.
30 years?
Yeah. Roughly.
And we as a team have been here now for a few years together, all of us. So, I just thought it was kind of interesting.
Yeah, the family.
The long time relationships here, so that we have in powdered metal. But so today we're going to talk about those frequently asked questions. And Joe, want to kick us off?
Yeah,
let's do it.
Go for it.
All right. And again, as I mentioned in our last episode, if there are topics you want us to cover, please let us know. Those are, we're willing to cover whatever it is that you want to hear about. So we appreciate you watching and want to keep you as a follower of our podcast. So if there's topics you want to hear, please let us know. Joe, what is conventional powder metallurgy and how does it work?
Well, Mark, as you know from our PM 101s that we do, the conventional side of things is one of the older styles of processing that are done, where you take granulated metal and you take a rigid tool and you fill that cavity to a certain level, compact it, and then sinter it. That's as opposed to many other ways of doing it. Metal injection molding, or MIM, is a common one. Additive manufacturing, there's spray forming. There's a whole series of other ways to use powders, but what we deem as the conventional method is a straight cold compaction, for the most part, of those metal powders into a cavity to a near net shape for the customer. That sintering process then bonds it, and theoretically, the part's ready to go.
Okay. Tom, what steps are involved in the powder metal manufacturing process? I know Joe actually just touched on a couple of those now. But
First of all, you have the powder. We have powder producers that make the materials, whether it's iron-based or non-ferrous, coppers, brass materials, bronze materials, those types of things. That's the way we receive the material in-house. Then we will and we can look at these probably later on through tooling. We have where we compact those materials into a shape, and Joe alluded to it. Then we sinter the material, and finally it can be done there, or you can just about like any wrought material, you can machine it, you can heat treat it, plate it. Those types of things.
In sintering, Tom, just what's a typical temperature we would sinter?
It depends on the material, but you're going to be in the 2,000 to 2,100 degree range for most of our iron alloys, and bronze is going to be more in that 1,600 degree range for your brasses and bronze materials. And then we'll do some materials, what we would consider high temp sintering above 2,100 degrees as well.
Okay.
So,
all right. Joe, you want to touch on some of the advantages of powdered metal over other machining processes?
Well, the main thing is the part that you get in the material that's in it, there's very little waste that goes along with that. So as opposed to other processes like a stamping or any other machining process or you end up having potentially a lot of loss. Where in our process, if you're part weighs 3 grams, we're putting 3 grams of material into that cavity and it's ejecting, and that's what you get. So the biggest advantage is you don't have all that energy loss from that aspect. So it's a very efficient process from that standpoint.
Okay. Doug, so what does typical tooling for powder metal parts consist of, and how long do those tools usually last?
Yeah, a typical set of tools, I mean, every set of tools is going to consist of a die and a top punch and a bottom punch. But I mean, the tools become much more complex as the part becomes more complex. You know, we can have a core rod that would put a center hole through the center. That could be round. It could be splined. You could have a series of satellite pins in there that allow you to put lightning holes in there. And of course, as the part gets more complex, you're going to get more levels, more punches on the bottom and or top. That allows you to compress a more complex part. So, but a very simple set, you know, you're talking about a die, a top and bottom punch. You know, we have one here on the table that's a pretty simple part, pretty simple set of tools. How long they last? Well, that depends. I mean, it depends on a lot of things. It could last anywhere from 100,000 hits, and we have some that last up to 1.5 million hits. Now, there are some things that happen throughout the life of that tool where we'll redress it. We'll redress face details that might get chipped or worn.
Okay.
So there is some rework that takes place throughout the life of that. Some of the things that will determine the life of that tool is what kind of powder you're compressing, the compressibility of the powder. You know, because powders that aren't as compressive, you know, will put more stresses on the tools and, you know, tend to lead to cracking or breaking. How abrasive is the material? You know, abrasive materials tend to want to wear out dies and punches more. The tool material selection that you choose, whether you have coatings or you can do some nitriding. There's a lot of things you can do to help improve the life, but a lot of it comes down to the geometry of the part. Right, if you have a lot of face detail on a punch that you're potentially overpressing, we call it, where you have a real high density in one area and low density in the other, you know, that tends to lead to cracking of punches. So the complexity of the part has a lot to do with the tool life as well.
I know we often get questions about prototype parts.
Mm-hmm.
And we do prototype parts and
Sure. Yeah, we do. There's 2 different methods that we use. I mean, one, we would build a set of tools and make prototypes. The other is that we would buy a powder metal puck and machine the prototype out of that puck. What determines which path we go is, one, how many parts do they want? If they want 5 or 6 parts, 10 parts, maybe it makes sense to do it out of a puck. You're kind of, at that point, you're weighing the cost of, you know, how much it costs to get a puck, how much it costs to machine it compared to the cost of of building that tool. The other thing is, I mean, if you want more than 10 parts, you want 20, you want 50, you want 100, then it makes sense to build that set of tools to make those parts. The good thing is that when we build a set of tools, that prototype set of tools ultimately becomes the production tools. There's really no difference. So, you know, whether you're going to build a set of tools or not goes down to essentially how many parts do you want. Mm-hmm. You know, and the last thing is how far along in the design cycle is the customer. You know, if they want parts that they're going to put on test and they're not really finalized with the design and they only want maybe 6 or a dozen parts, it makes sense to do it out of pucks. But if they're far enough along in the design phase that we say, all right, then there's really no risk to build a set of tools because ultimately they'll become a set of production tools.
right.
There's a lot that goes into that.
And along with that, what he's alluding to is long enough in the design phase that the basic dimensions of the part aren't going to be altered a lot. If you're going to move something, say a customer's not set on an outside diameter and they're going to move it 10 thousandths, well, that tool's no longer going to be any good for us.
Right.
But if they've got those features tuned in enough that they may only have some maybe face detail or some other minor things that they're adjusting, that's when it makes sense to go that route.
Another thing that would be like material selection. If they're not finalized on a material selection, building a set of tools might not make sense because, that every powder has a dimensional change to it. And if we build a set of tools to suit for one particular material, and then they want to switch to a different material. If it has a different dimensional change, we're not going to be able to hit the dimensions. So, if they want to try several different materials and they want, 6 or 10 parts from different materials, sometimes it makes sense to machine them out of pucks. So, before we invest in building a set of tools.
And as you know, Mark, those are the kind of conversations we have with you guys and the customers to say, this is what limitations we see for you. And that goes back to their print. If we think the tolerances are open enough that we're not as concerned about if they shift a material, we'll let them know that. But if we think the tolerances are too tight for us to make that change and we've got to make the commitment, that's when we kind of guide them to either a puck or a tool, depending on those circumstances, because we don't want the customer wasting money.
Right.
So we're going to make the recommendations. We think that they have, ultimately it's the customer's decision. They tell us what they want to do.
Mm-hmm. Well, speaking of that investment or cost for tools, and I know, Doug, it can range. I'm sure there's a wide range of price, but what do a typical set of tools like?
A simple set of tools that's sitting on the table, that there is a single level top, single level bottom part that's about a half inch. It's probably, maybe $4,000. Mm-hmm. Maybe sometimes less, but as you get into having multiple levels, a couple things happen, right? You're adding punches to the bottom and or top, and as I add those punches, they're getting longer too because I'm going deeper into the die set. So all that plays into it. Your material costs go up. You're machining it. You're more machining on that particular tool. So we have tool sets that range anywhere from $3,000 to $4,000 all the way up to $20,000 or $25,000.
Yeah.
And the size of the part has a lot to do with it too, because, the size of the part, the bigger the tools, the more, the more cost of the material, for that tool. So the ones that I'm talking that are 20 or 25,000 are probably 600, 700, 800 ton parts, parts that go into a much bigger press.
Right. And I guess the reason why I asked, Joe, is I know we talk about tooling and other processes could be even more expensive than that. So I just kind of wanted to give a guideline and say, tooling for powder metal isn't maybe as pricey as some other processes.
Correct. And going back to what he just alluded to, the tools that we have an example of sitting here are single cavity. Most tools that we produce are single cavity. A handful of times, 2 cavity, maybe 3 cavity, but most things are single cavity. Because the speed that we're going to produce is so fast, we can outrun whatever a customer needs in a single cavity. And it downsizes the press size. Where if you have a plastic tool or a metal injection molded tool or a casting tool, you're going to have multiple cavities in most of those cases, and each one of those has to have that intricate form.
Right.
And so we're doing a one-off. They're doing multiples, but we're able to keep up and exceed the speed of what our customers' needs are in those cases.
Right. Phil, what is the typical size range of parts that we can make in PM?
Well, in the plant, we have presses ranging anywhere from 15 tons to 825 tons. The size, what determines the size of a part we can make is also the size of the part plus tonnage. Surface area usually depends on how much tonnage we're going to press, but we'll usually run out of tonnage before we run out of. We usually run out of size before we run out of tonnage. We'll usually hit the tonnage mark way before we get to a part that's too big for the press. Some things we can do to bring that tonnage down is eliminate some of that surface area by putting, like Doug had said before, lightning holes or something to that effect to take some of that material out, take some of that surface area away, because the surface area is what drives that up. So some of the other issues that we might have is that we don't have, that maybe some other customers do have, is the 825 ton presses that we have are we have more than one level. We have 3 levels in the bottom and 2 levels in the top. We do have other presses that we have 4 levels in the bottom and 3 levels in the top. So that also comes into play also. But 825 is the highest press that we have in the plant right now.
Okay. So I guess, Phil, just kind of explain what a powder metal conversion is. We get that question oftentimes. What is a conversion and why can it be a game changer, so to speak, in manufacturing?
We do have customers that come to us or sales goes out and they talk to them about, they make parts out, they're getting parts made now out of wrought steel, where we all know machining is very expensive. So you get a piece of wrought steel and you whittle what you want out of that. The price of that part is very expensive. We can actually make parts near net shape to where either eliminate or reduce the amount of machining that is done to that part, which makes the parts a lot cheaper than what they can get now. They might get parts that, like the part there, with the splines on it. That would be extremely expensive to be made out of a wrought steel part. And I'm not sure if maybe it was at one point. But we make that out of powdered metal now, which saves a lot of money. I mean, you don't have to cut the teeth. We mold the teeth in. That's got to be a huge expense when it comes down to the difference between a wrought steel part and converting into powdered metal.
And back to the speed with which we do it. If you're going to machine that part, you're talking minutes.
Oh yeah.
To do it, we're going to mold the part in seconds. Yeah. So the speed with which we can produce a part is much faster.
And the parts are lighter. I mean, the parts that we make are not fully dense, but are strong. Some of them are strong or stronger than a fully dense part. So we can make the parts that actually come out. They'll be actually lighter than the part that they have now.
Oh, okay.
And other types of conversions are castings, right? If we convert a casting to a powder metal part, some of the advantages are we can hold a much tighter tolerance than you can on a casting. We don't necessarily need any kind of draft. Like they have a lot of draft to be able to get, maybe on a casting for it to release, whereas we don't always need that draft. So it's just less machining and, tighter dimensional control if we would convert a casting.
And it comes down to too is scrap. There might be more scrap when it comes to casting because of inclusions that we don't have that issue. We don't have to worry about inclusions in the parts.
Okay.
And back to, I guess, what you were talking about, when you look at a part, or when we look at a part, it's not just the part we look at quite often. We'll look at the subassembly, because in many cases, a customer is making a subassembly because that's the easiest way to make a portion of it. In our case, we may be able to produce the entire subassembly all as one component and not have to build the 2 or 3 components.
We might have an example of that right on the table.
We think we do. I think we have one of those right there.
I think we do. Tom, how is porosity used to enhance the performance or functionability of a PM part?
Yeah, generally, and the industry really started in the bronze bearing end. We make a lot of self-lubricating bearings. So when we make the part, we mold it, we sinter it, and then we go through what we would call a sizing operation to bring it into its final dimensional tolerances. And then we take and place that in an oil bath and draw a vacuum down and fill those pores with oil. And after it's impregnated with the oil, then assuming everything's designed correctly, that bearing should last the life of the product that it goes into. So if it's going into a motor and it starts to heat up, the oil becomes viscous and will prevent the galling of the bearing. And as it cools down, there's a capillary action that draws the oil back into the bearing. And so through the design process, that will last the life of the product.
And Tom and I are kind of laughing at one another because when cost cutting becomes a fun time for everybody, one of the places they always want to cut is the copper components, or the bronze bearing in our case. They want to make the walls thinner and thinner and thinner. And what they don't realize in those cases is our product is not only the bearing surface, but it's also the oil reservoir. But you start to cut that wall thickness down, you no longer have the oil to then feed the system. And now you have to feed the system some other manner. So they have to turn around and add a wick, or the customer has to oil it more frequently because they've reduced their capacity in the component. So it's, Tom and I have lived through that, where we used to have a nice thick wall on something and it kept just getting thinner and thinner and thinner. And you just sit there and go, well, you just defeated the purpose of what you were trying to do.
And depending on the application, there are some alternatives to that. High graphite iron materials work well as a replacement at times for bronze bearings. Those types of things will help.
Those actually would probably be a cost savings.
Yeah, yes. And we can impregnate with some greases for some applications. We've done that with customers. So those are the ways that we basically can utilize the porosity in the pores in the part.
Okay. Joe, we're fortunate here, as you know, to have a couple steam treaters in-house. You want to talk about what steam treating is and how it's used?
Well, Mark, I believe we've talked about steam treating in a couple of our items in the past. But so if a customer wants to go a little more in depth, they can go on our website and find some details of that.
So you're saying you don't want to talk?
No,
That's what I was going to ask. What's
I'm just kind of
waiting at a question?
This is going to be a brief answer to a much bigger topic. So if they want more details on it, we have information on our website for that. But basically what it is it's a process where we take the part, and it's a furnace for all intents and purposes, where we increase the temperature to about 1100 degrees. And then we introduce superheated water or steam into that. And it then creates an oxide layer on the surface of the part, converting that. And it can also build an oxide layer and fill up some of the pores as well. What ends up coming out of that, and we have an example on the table as well, what ends up coming out of it is kind of a gray to bluish tint that is corrosion resistant because it is an oxide layer already. It doesn't readily want to convert to a red rust at that point. It acts as a wear layer, because the hardness of the particle of that oxide that's created is also very high. And so it's a common thing for us to do that most other industries won't utilize.
Okay. Tom, I'm going to ask you a question about copper infiltration.
Oh boy.
I wonder if we probably covered this in another episode. But if you would, please give us, your answer about what copper infiltration is and why we use that.
Well, it's generally used to increase strength in the compact, some elongation increase in the material. And so what will generally happen is we will press a iron component, and which we would call at that point the skeleton. And we take a piece of copper material, either pressed or wrought type of copper material, and we place it on top of the part. And what happens is, because the part is not fully dense, there are pores throughout that part. As it heats up in the furnace, the copper melts. And as we talked about with the bronze bearings, there's a capillary action that draws that copper into the compact. And then when it comes out, the pores are filled with copper.
Okay. Joe, can a finished powdered metal part be used in a welding application?
It can, yes. It is done all the time. There are many applications that we have had over the years that customers will weld the component. It can't be treated like every other stamping in wrought part per se, in that you have to be very careful. And I'm assuming when you're going to weld a stamping or you're going to weld any other material, you have to make sure it's clean. Well, what you have to do with our product is it's going to arrive clean, and you can't let it get contaminated. So
I've heard your story many a time.
Tom alluded to the fact that there's a capillary action. You put arm parts near contaminants, whether it be waters or lubricants or anything like that, it will absorb it, and that will inhibit an off gas during the welding process. So you keep it clean, and there is no issue at all with doing a welding to a powdered metal part.
Okay. I guess I'll just ask the entire group here, what factors influence the cost of powder metal part? And I know we've kind of talked about a lot of these from your, but what are some of those factors, Phil?
Machining is a huge cost. I mean, we like I said, we make parts that are near net, but there's always some machining costs that have to happen. So we always try to eliminate that as much as possible. Machining has always been an expensive process, and it's always going to be. So we really try to reduce that as much as possible.
I would say part geometry. It's a case by case basis that you're looking at it. Every part's a little bit different, but, does it have thin walls? How many levels are on it? How complex are the face details? And I think of it from a tooling standpoint. I'm a tooling guy, and when you talk about tool cost and tool maintenance, the first thing I do when I look at a part, that's what enters my mind. How are we going to tool that? How are we going to maintain those tools? How long is the tools going to last? So for me, it's the part geometry.
Yeah.
Those are two of the big ones. And going along with that is the handling of the product, how quickly it can be molded and how it can be handled coming off the molding press. If you have too thin walls, it tends to be a concern because now the part's coming off that press, and it's still relatively fragile when it's coming off that molding press until it's been sintered. And that handling can have a big play in that and how you can deliver it to the furnaces in those cases.
Material, Tom?
Material certainly depends whether it's copper or iron, or certain iron alloys are more expensive than other iron alloys. Density, to me, is a big driver for cost in our system. Everybody wants to kind of look at the book and pick out the highest and the best. You need to design for what you need, because the higher the density, the more wear and tear you have when you're tooling as you're making that part. So optimize that in the design process, and you can help control some of those costs.
And Joe, how does volume play into that as well?
Well, volume comes into it. As you know, Mark, we don't have a volume restriction internally for most customers, but
right.
From a practical standpoint, if you're in ultra high volume, if you're in the millions of pieces, that's not an issue. When you get down below 1,000 pieces, you start to now get to the point that there's a base cost to set up that press, run the parts through the furnace. Mm-hmm. Just the time that you have in that, obviously that becomes the driving factor rather than the weight in the mold cycle itself. That's not the big thing. It's just the setup costs that come into play. But, we work with a customer on that. It's a balancing act, because though we may look at it and go, it's costly, the alternative to machine it or manufacture it in some other way, we may still be less expensive. And that's why we do a lot of low volume stuff for folks as well.
Right. Yeah, I know. Just for my customers alone, I have customers that will make 500 parts a year. And then we have ones that will make 14 million parts a year. So, but there's a wide range.
Yeah.
I know volume certainly does play into that overall piece price.
Sure.
So, Sure. All right. Well, listen, I want to thank you all, and thank you for watching today. If we didn't cover your question, again, please let us know, and we'll be happy to. Joe and I jump on Teams meetings all the time. These three are often in those Teams meetings as well. So we'd be happy to answer your questions via Teams, via email, or again, we'll cover it here in our next episode of the PM Blend. Thank you again for watching. And again, please follow our socials.